Everyone. We're just getting started, waiting for a few more people to get on the live stream, and then we'll go ahead and start discussing waves today. As usual, please also log into the Zoom, and we're going to sort you into breakout rooms too. So make sure you accept your invitation for going to a breakout room. Sometimes it's behind all of your other screens, but please accept that so that you can work in groups. Okay, we'll give it another 1 or 2 minutes for a few more people to get on, and then we'll go ahead and get started today. How many are in the Zoom? Okay, great. So we're going to go ahead and get started today. Okay, so this week we wanted to discuss properties of waves and some wave physics. So first off, why study waves? You know, this is chemistry. But in chemistry, we actually use waves to represent matter. So everything from electrons to mass, we can all represent using the mathematics and physics of waves. So because this is one of the fundamental building blocks of chemistry, your Chem 1A class will actually start out teaching you this semester by solely discussing waves first. And then they will use the fundamentals of waves to relate that to the electronic structure of atoms so that you can understand how atoms behave. So our goal of the last few days of week 3 is to help introduce you to some of these concepts so that hopefully you guys can all get off to a great start in Chem 1A. So first off, what actually is a wave? So a wave is a periodic disturbance that travels through a medium. And a medium is just any substance that carries a wave. So for example, in this example with the rope, it would be a rope. And the important thing to note about waves is that they transport energy, but they do not transport matter. So if you think of this duck floating on top of a wave in the ocean, The duck is slightly disturbed by being on top of the waves, but it always comes back to the same position. So although there is some local motion, there is no net movement of the duck. The duck stays mostly in the exact same spot. However, energy can still be transferred. So this is different to other forms of energy, like kinetic energy, for example, where if you had a baseball bat, you swung it and hit a ball, the ball would then move, right? So the distinction that what makes waves so special is that they only transport energy, but they do not transport matter. So if you ever get confused about that, just think about a duck floating on the waves. It's always going to stay in approximately the same spot, and there's no net movement of the duck. Okay. So we can also think about how waves propagate. So the interactions of particles is actually what allows waves to move. So on the top, we have the person creating a disturbance in a rope, and that moves through like a wave, but you can also think of this as individual interacting particles. So in the video right below the rope, you see all of these little dots. And as these little dots move, they affect the other particle next to them. So it's these interactions between particles that allows disturbances to travel through a medium. And again, I would just like to emphasize that although particles are temporarily displaced by these interactions, there is no net movement of matter. Okay, so someone asked in the chat, are waves always continuous like the graph you showed in the last slide? Yeah, waves are always continuous. So you can usually always represent them with a continuous math function. You can split them up in ways that makes them feel discrete, but they are always continuous. Okay, moving on. So we can also talk about two different types of waves. So we can categorize waves based on the overall direction of movement of the individual particles compared to the direction that the wave travels in. So if you think of this slinky, as you move the slinky up and down, you get a transverse wave. So in this case, the overall wave is moving from left to right, but you can see that the displacement of the slinky is actually moving up to down. So that makes this a transverse wave because the medium, the slinky, moves in a direction perpendicular to the direction that the wave moves. The other example is a longitudinal wave. So in this kind of wave, the particles move in a direction parallel to the direction that the wave moves. So if you see the example on the bottom with the slinky getting compressed, you see that all of those slinky parts move in the same exact direction as the overall direction of the wave. So it's convenient to think of these in terms of slinkies, but we can also think of them in terms of particles. So here I've shown a few more animations. So this time on the top, we have a longitudinal wave. So if you look at the red dots, you see that the red dots move left to right, and you see that the overall direction that the wave is traveling also moves left to right. So because the particles move in a direction parallel to the direction of the overall wave, that makes this a longitudinal wave. And on the bottom, all of these particles in the wave are moving up and down, but the overall wave is still moving left to right. So that makes that a transverse wave. So next, we wanted to talk about a few parameters that can help us describe waves. So first off, we can define a wavelength, and this is commonly denoted with the symbol lambda. So the wavelength is how far the wave has traveled in one cycle, and this is always in units of distance. And what we mean by one cycle is how long it takes the wave to come up to the exact same position. So I've denoted on this diagram blue dashed lines that separate off one cycle. So at the beginning, you see the wave is at the top or the crest, then it goes all the way down to the trough, and then it comes all the way back up to the crest. So because it's returned to the original position, that means that it has traveled one cycle. So that's how you would define a cycle in terms of wave parameters. And then the wavelength is just how far that wave has traveled in one cycle. And we would always express this in units of distance. For example, in this plot, we've plotted this against meters. We can also define the amplitude of the wave. So the amplitude is defined as the height of the wave from the center line. So here in the dashed lines, I've denoted where the center of the wave is, and then where the trough is. So that distance between the center and the trough is defined as the amplitude. So we can also plot waves as a function of time. So in the last example, I plotted waves as a function of distance. However, waves are functions of both distance and time. So for example, in this plot, now we see the oscillations as a function of time. And now we can define a few more parameters that describe how waves move in time. So the period is the amount of time it takes to complete one wave cycle. So again, if we sectioned off one cycle with blue dotted lines and then measured how long it took the wave to return back to the initial starting point by reading off of the axis, we would see that it took this wave around 7 seconds to return from crest to crest. So that means that this wave has a period of 7 seconds. And for some reason, period is always denoted with a T. I don't know really why, but that if you ever see a T in reference to a waves, that is always in reference to the period. So in this case, we would say that the wave makes one cycle every 7 seconds, or the period is 7 seconds. We can also define the frequency. So the frequency of the wave is the number of cycles that are completed in a certain amount of time. So again, we can measure how long it takes to complete one cycle of the wave. So just as we saw before, for this example, we complete one cycle every 7 seconds. But this time, we're not asking how long a cycle is, we're asking how many cycles happen each second. And that you can define by dividing the total number of cycles divided by the length of time of each cycle. So then you would get your frequency equals one cycle divided by 7 seconds in this case, or 0.14. And when we talk about frequency, it's often convenient to define a new unit. So in this case, often people use the unit of hertz. So 1 hertz is defined as 1 over seconds. So if we wrote this properly, we would say that the frequency was 0.14 hertz. So I'll briefly stop here in case any people have any questions about these different wave parameters. If not, we'll move on to a quick concept question. Oh, can you briefly explain the longitudinal and transverse waves again? Okay, let me go back to the pictures. So for me, the one with the slinkies is often the easiest to picture. So at the top, in the transverse wave, as you're moving the slinky, you're moving it up and down like this, right? So you're creating a displacement in the actual slinky that's moving up and down. But then the overall wave is still moving left to right. So because the direction that the slinky is moving in is perpendicular to the overall direction of the wave, you call that a transverse wave. So that would just be the definition. And then on the other example, you can think about like compressing a slinky. So if you were like just shoving it, that would create a motion of the slinky that's going left to right. And the wave would also move left to right. So because that direction is the same as the overall direction of the wave, then it's called a longitudinal wave. So I had two examples just because it can be helpful to think of them just depending on how people think. So in this, if you think of particles in this case, the top example is actually the longitudinal wave. So in this one, they've actually labeled the particles red. So you can, if you look at one of the red particles on the longitudinal wave, you see that it is moving left to right. And then if you look at the overall wave is also moving left to right. So that would make it a longitudinal wave. And then if you look at the animation right below that, again, that wave, if you try to pick out one individual particle in that animation, that particle would be bouncing up and down, just like how that duck was in the example before. But then the overall wave, we still define as moving left to right. So because the particle is moving up and down, but the wave is moving left to right, we call that a transverse wave, because the direction that the particle is moving in is perpendicular to the direction that the wave moves in. Does that make more sense? Here. Maybe I'll go to the duck one briefly in case that helps clarify. And also because it's a pretty cute duck. Okay. It's not updating.
Difference between wavelength and period.
Okay, great. So someone asked what's the difference between wavelength and period. So you can plot waves as both functions of distance and time. So when we're talking about a wavelength, we're talking about how much distance has been traveled in one cycle, right? So that would have to be in some units of distance, like feet or meters. Whereas a period is how much time it took a wave to complete one cycle. So that would always be in some units of time, like seconds, minutes, hours. So they're both the same in that you're seeing how long it takes one cycle of a wave to do something. It just depends on what you're plotting the wave against. So waves are both functions of distance and functions of time. So the wavelength parameter describes how waves behave in terms of distance in meters, and period describes how waves behave in terms of time. Yeah, so they're very similar and they're closely related. So we'll actually talk about how they are related later in the lecture. Okay, great. So continue asking questions in the chat, but then also take a minute in your groups and look at these two waves, the orange one and the greenish blue one, and discuss which wave has a higher frequency. And I'll give you about a minute to do this. And I also have the definition at the bottom that frequency is defined as the number of cycles that are completed in a certain amount of time. Yeah, longitudinal waves are also called compressional waves. Okay, so I'll go ahead and go over this quick concept question. So frequency is defined as the number of cycles that are completed in a certain amount of time. So if your wave has a higher frequency, that means more cycles are completed per second. So it oscillates more. And then if your wave has a lower frequency, that means fewer cycles are completed for a given amount of time. So that means that the top example has a high frequency and that the wave on the bottom has a low frequency. So hopefully that makes sense based on what we discussed in the previous example. But again, feel free to post in the live chat if you have any questions. Okay, so we can also define the velocity of the wave. So the velocity is just the speed of the wave as it moves, and this can be dependent on a lot of things. For example, the type of the wave or the medium that the wave is traveling in. So just like we do in physics, we define velocity as distance divided by time. So if you consider one cycle of a wave, what parameter describes the distance? That would actually be the wavelength. So we talked about earlier that the wavelength is the distance the wave will travel in one cycle. So we can use the wavelength to represent distance. And then the period is also the amount of time it takes the wave to complete one cycle. So that means we can represent velocity in terms of the wavelength of the wave and the period of the wave. So I've written that out here. And then the period of the wave and the frequency are also inversely related. So that allows us to simplify this equation into what we kind of commonly represent in wave physics. So another way of writing wavelength divided by period is wavelength times frequency, or lambda times f. So this is the way that you'll commonly see it written in textbooks, but remember that that is the exact same thing as wavelength divided by period, and that is also just another way of saying distance divided by time. So although we've defined all of these new words for waves, at the end of the day, our wavelength is a measure of the distance that the wave has traveled, and the period is a measure of how much time it took the wave to travel. So that means that we can just get velocity from distance divided by time, or the wavelength divided by the period. And we can also go back and use units and dimensional analysis to check that this is actually true. So for example, wavelength is a unit of distance, so for example, meters. Frequency is 1 over second, and if we multiply that out, that means that velocity must be meters per second. And we know that velocity has units of meters per second, so that's a good check that this equation makes sense. Okay, so now in your groups, do a quick practice question. So I'd like you to find the velocity of a wave in a wave pool if its wavelength is 3.2 meters and its frequency is 0.6 hertz. So I'll give you about 2 or 3 minutes to do this in your groups, and feel free to also post questions in the chat and I'll try to answer those as well. Does anyone need more time for the example? If not, we'll go ahead and get started in 1 more minute. Okay, great. So I'll go ahead and go over this practice question. So we can write velocity in terms of wavelength and frequency. So like we discussed on the last slide, velocity equals wavelength multiplied by frequency. So in this example, we were actually both given wavelength and frequency. So what we would need to do is multiply 3.2 meters times 0.6 hertz. And that would give you a velocity of 1.9 meters per second. So as a reminder, a hertz is another way of writing 1/second. So that's why these units at the end work out to be meters per second. So just keep that in mind. Okay, so we can also represent waves mathematically. So if you look at this video of a wave in the ocean, and then you pick one particle and you trace its behavior, you can see that that particle actually moves in a circle. So for every particle in a wave, we can represent that motion with some geometric shape. So some of you may have seen this before in geometry class, but you can also represent this circle using what's called a unit circle. And this helps you relate the motion of the wave to the unit circle. So this is really helpful to map waves to mathematical functions. For example, one of the common functions that we would use to describe a wave is actually the sine function. And we can write waves using the sine function in a way that allows us to understand their wave parameters. So on the bottom, I've written out the equation for sine. And you see at the beginning of the equation, there's that constant A. So in that case, that A represents the amplitude. So that multiplier, you can always read off, and that will give you the amplitude of your wave. And then similarly, your wavelength will be represented in that angle term of the sine function. So we don't expect you to know all of the ins and outs of geometry. We just want you to kind of understand that you can think of waves in terms of math, right? So we do have these repeated periodic functions, and in many cases we can represent them using sines and cosines, for example, and that sines and cosines can be represented using something called a unit circle. So this isn't the math class, but this is sort of the basics you'll need in Chem 1A to be able to talk about waves. So the main part is that you can represent waves using math functions. For example, the sine function is the most common one. Okay. So waves are also additive. So say you had a green wave traveling through your medium, and then that wave encountered a blue wave. So what would happen? So waves are perfectly additive. So if you take the amplitude of the blue wave, the amplitude of the green wave, when these waves pass each other, you would get a new third wave that would have the amplitude that's the sum of the individual component waves. So that would be the red line, which is the exact same height as if you added up the height of wave 1 plus the height of wave 2. So this is a really important property because that means then if you ever want to know what will happen to a wave that interacts with another wave, you simply just need to add their different amplitudes at every single point, and then you would get your new wave. So just to go through that one more time, because this is a pretty important concept moving forward, say you had a blue wave moving through a medium, and that encountered a green wave. So you would ask yourself, what new wave will result because these two waves are interacting? So we know waves are additive, so we would just need to add the height of the wave or the amplitude at every single point, and that would give us the height of our new wave. So for example, you would take the height of the blue wave, the height of the green wave, and then you would add those together and you would get the height of your new wave, which is the red wave. So someone asked, what's the formula to represent waves as a period, and is it typically described as a function of wavelength instead of period. So the formula would be, that formula that I showed was in terms of distance, so that's why the parameters were wavelength. So you could write the same things in terms of time, and then you would have the period in terms of your function. So someone also asked, can we still add waves if they have different frequency? Yeah, absolutely. So we'll do an example later in like a demo where you can play around and add waves with different frequencies, but they absolutely will still add. So if their amplitudes don't line up perfectly, maybe it makes the math a little harder, but it's still perfectly additive. So yeah, you would still add it up just like you do in this example. It would just be a different point on the wave. But hopefully that'll be more clear in the demo that we'll do. Okay. So multiple waves interacting with other waves is called interference. So there are two main types of interference. So one is called constructive interference. This occurs when the two interacting waves have a displacement in the same direction. So for example, we have this blue wave approaching this red wave. And you can see that their displacement is both in the positive direction. When these two waves meet, you would add up their total displacement. So now their height would be the sum of the blue wave's height plus the sum of the red wave's height, which in this case we could just represent as 2x. So that would be an example of constructive interference because the interacting waves both had displacement in the same direction. So that means that your new wave basically has a larger displacement than the other wave. So you can also define destructive interference. So this occurs when interacting waves have a displacement in the opposite direction of each other. So let's consider again our blue and red waves. So for example, you have this blue wave that is traveling towards this red wave. The blue wave has a positive displacement and the red wave has a negative displacement. So when they actually meet, they would cancel each other out because they are going in opposite directions. So it would be positive x minus x equals 0 would be the way that you could represent that if you wanted to think of it in terms of equations. So this is called destructive interference because these two waves basically destroy each other, right? Whereas in constructive interference, they build each other up. In destructive interference, they have this opposite displacement, so they destroy each other. Okay, so now in your breakout rooms, if you could all take about 5 minutes and go to this link. So we'll go ahead and post that in the breakout rooms and also in the live chat. But this will answer a lot of the questions about what happens when you add waves if they have different frequency and what if their amplitudes don't line up. So when you go to this website, there's a demo that you can click on and basically control all these different parameters like, amplitude and frequency. And then you can see how adding these different waves changes the third wave. So I'll give you guys about 5 minutes to explore that in your breakout rooms. It's a pretty cool animation. Okay, so someone asked, will you ever get a problem in a test in which you have to add waves with different frequencies? If so, how would we do that? So the answer is that in chemistry, no one will probably ever ask that of you. And I don't think anyone in physics ever asked me that. I think that they would never give you like the fun. I think that that would only happen in a physics class after you had learned how to do it. So I wouldn't worry too much about that now. Um, but if you did want to add them up, you would just have to take the different points and add them up. So hopefully it wouldn't be too hard, and it should be exactly the same as what we did with the simpler examples where the waves were perfectly synced up. But they still are perfectly additive. So you should just be able to add the functions together, or always just add up the points, and then that should always work out. That's a mathematical principle actually that's specific to waves, and we'll talk about that at the end of class. Do we use any other functions besides the sine function to represent waves? So yeah, you can use a lot of different functions. We're just going to talk about sine because that's the most common one in chemistry. But there's you can have square waves and things like that. So there are many mathematical functions that can represent waves. Yeah, someone says transverse plus longitudinal looks cool. I agree, that's a pretty cool demo. I hope you guys are all enjoying it. Do you guys want a few more minutes playing around with the demo, or should we go ahead and move on? If you're still learning from it, then we can give a few more minutes. Okay, a few more minutes. wave did you? Yeah, Lorena's been making some pretty cool waves too, so.
That's so much fun.
You can make it full screen too if you click the arrow.
Ooh.
Yeah.
It's like a little wave dance party.
Okay, I'll give you guys another minute and then we'll go ahead and move on to something that's probably less fun, but only because this wave demo is pretty cool. That's so cool. Okay, great. So please wrap up your demos. We'll all come back together and go over some more information about waves. But if you're ever confused thinking about what some of these different parameters mean or about interference, definitely go back to this website. Wave physics is really complicated, so it's nice to kind of break that down into pictures to see what is actually going on. So definitely use this as a resource. Okay, great. So this brings us to the principle of superposition. So that's a big word, but basically this states that when two waves interfere, the resulting displacement of the medium at any location is the algebraic sum of the displacements of the individual waves at that same location. So that's a long way of saying that waves are always additive. So if you have two interacting waves, no matter at what points they interact, that's always additive, right? So someone asked, what would you do if the waves don't perfectly line up? You would still just add them. So you would take every x value and you would add the corresponding y values of those different waves, and they would always be perfectly additive. So this is a really important concept in wave physics and linear algebra. So this will probably keep coming up as you kind of proceed through some of your college coursework. But just keep in mind that in chemistry, this is really important because it basically allows us to add up waves as the sum of their individual components. Okay. So I also wanted to talk about electromagnetic waves. So these are a special class of waves, and electromagnetic waves are made up of an oscillating electric field and an oscillating magnetic field. So by definition, these two waves will always be oscillating perpendicular to each other. So that comes from physics. As engineers, you'll all be required to take the physics on electricity and magnetism that describes this in more detail. But for our purpose, we just want to understand some of the properties of these waves and relate that to chemistry. So the important thing to know is, one, electromagnetic radiation consists of these oscillating perpendicular electric fields and magnetic fields. But otherwise, you can define everything else exactly the same, like their wavelength, their frequency. That's the same as any other normal wave, right? And electromagnetic waves can travel through empty space. So they don't need a medium. They could travel through a vacuum if they wanted, which is kind of cool. So we can commonly plot the different types of electromagnetic waves on something called the electromagnetic spectrum. And commonly you'd see this plotted as a function of wavelength and of frequency. So at the top we have radio waves. So these are the ones that have the really, really long wavelengths. So when you're listening to the radio in your car, it's actually electromagnetic waves that have wavelengths around 10 to the third meters. That's what is carrying that energy and information that allows you to hear music. And then you can go all the way down to really, really small wavelengths. For example, visible light is on the order of 10 to the minus 6. And that's actually a really, really small region of the entire electromagnetic spectrum. And you can go all the way down even smaller to X-rays or gamma rays that then have wavelengths that are on the order of atoms and atomic nuclei. So you really are spanning distances all the way from buildings to atomic nuclei, which is kind of cool. And similarly, you can also plot frequency. So frequency and wavelength are inversely related. We'll talk about why on the next slide, but you can also plot these different kinds of waves as a function of frequency. Okay. So all electromagnetic waves travel at the speed of light. And the speed of light has been measured to be 3 times 10 to the 8 meters per second. And as we talked about before, the velocity or speed is related to the wavelength times the frequency. And here I wrote frequency as V, just because that is also commonly used to represent frequency. So I apologize for not keeping it consistent in my slides and writing it as an F, but it is the same thing. So that is wavelength times frequency equals C, which is the speed of light. So because of this equation, you can see that wavelength and frequency are inversely proportional, because you know that all electromagnetic waves will travel at the same exact speed. All of them, no matter how long their wavelength or how high their frequency, they all will travel at the exact same speed of light. So because of this, that means if your wavelength goes up and you have to always be moving at the same exact speed, that your frequency must go down. So that means that the wavelength is inversely proportional to the frequency, which is something that you can see in this plot, and that's something that you can also get from looking at the equation as well. So as a quick practice question, please in your breakout rooms take like 5 minutes to do the following question. So say a radio station broadcasts at a frequency of 590 kilohertz. What is the wavelength of the radio waves? And then your hint is that the speed of light is 3 times 10 to the 8th meters per second. So take around 5 minutes to do that, and feel free to still post any questions in the chat and we'll answer those as well. Okay, I'll give everyone another minute. If you need more time than that, definitely post in the chat and we can wait a few more minutes. Okay, great. So we're going to go ahead and go over this example. Okay, so we know that wavelength times frequency must equal the speed of light. So in this problem, we're asking for the wavelength. So you could rearrange that equation and write wavelength equals speed of light divided by the frequency. So in this case, you would have 3 times 10 to the 8th divided by 590 times 10 to the 3rd hertz, and that would give you 500 meters as your wavelength. So hopefully everyone was able to get that okay. Okay. So tomorrow we're going to continue talking about energy and waves, but now that we have some of the fundamentals down, we're going to start exploring how this relates to chemistry. So we're going to talk about how you can calculate the energy of electromagnetic waves and how waves transport energy. And then we'll also talk about how you can learn about atoms by analyzing these differences in energy that are caused by waves interacting with matter. So definitely please also come tomorrow to both the live stream and the live breakout rooms, because it's really helpful if everyone is all in class together so that we can work through examples together and kind of help everyone learn. So yeah, that was all we had for lecture today. So please stay in the Zoom room for our office hours, and again, happy to answer any questions via email or office hours as well.